Previously, we talked about how to replace the Newton method in the implicit solver with iterations of a fixed point method. This fixed point method is based exactly on the implicit differential equation solver that we have figured out. So this morning I want to look at how that goes exactly. Everything is the same as in our preceding work, except for one thing. In the main body of the program, instead of calling subroutine solve x, I'm going to call subroutine solve x2. Solve x, you'll remember, was based on our implicit differential equation solver together with Newton's method. By contrast, in the solve x2 routine, there is no Newton method. As before, we get an initial estimate for W number I plus 1 by doing one step of Runge-Kutta. After that, this is the work in the subroutine. I decided arbitrarily to do 10 steps of fixed point rather than Newton, and if you'll take our differential equation method and replace Wi plus 1 with x, you will get that line of code. This is our implicit differential equation solver being used as a fixed point method. As usual, initially I'll give it 123 subdivisions. Let's look at the errors. This will be the difference between the computed solution and the exact solution. And as you can see, the errors are comparatively small, and as we go along, they maintain a certain consistency. It might be worthwhile to actually draw the graph on this one. Since I've forgotten what I called the files, I'll just run it again quickly. I'll look at AM solution and exact. And as you can see, there's pretty good agreement between our computed solution and the exact solution, just as it should be. I want to investigate how rapidly the fixed point method is converging. This step of a fixed point method has to be done for each new x value that I'm calculating. So let's see how the details go. You'll notice here that the difference between the current x and the corresponding wi plus 1 begins life as about negative 1.98 times 10 to the minus 3 power. After one step of the fixed point method, that's reduced to 1.813 times 10 to the minus 3 power. And if you look at the consequent numbers, by the end of the very first step of my differential equation method, The error between the computed estimate of wi plus 1 and the exact solution value yi plus 1 apparently has settled down to a good number of decimal places. There is still a discernible difference. If you look at these numbers, the digits are different after this. This might indicate that I should run the differential equation solver with the same settings, but possibly do more steps of the fixed point solver in solvex2. Also, it might be interesting to see what the effect of making the number of subdivisions larger, which will make dt smaller. I'll give it 10 times as many subdivisions. As we had hoped, the solution that we calculate is considerably improved over the other one. We were getting numbers in that last column that were about 10 to the minus 3 during the first call to solve x. Now, using solvex2, that's down to 10 to the minus 5, which is much better. Let's just scroll down quickly to make sure the errors don't mount up on us and run out of control. I gave it 1,230 subintervals. So we're about halfway through now, and everything seems to be pretty nice. There appears to be no problem at all. So this fixed point idea, it certainly seems to work. A more sophisticated idea might be to use, to get started, some highly accurate explicit method, a method that uses only wi and previous w's in order to get an estimate for wi plus 1, and then use that estimate as the input into one of these fixed point implicit methods. Ideas like that form the basis of what are called predictor-corrector methods. We'll talk about that in our next short video. I hope everyone's having a good day. We seem to still have computer issues with D2L. Remain calm. We'll figure something out.